Hey everyone, today we're going to talk about function inversion. When a function reaches its entire codomain and satisfies this property called being injective, which we'll talk about later, we can construct its inverse function. What does that mean? Well, given such a function, we'll say f from a to b, and we'll assume that it satisfies these conditions we just talked about. We'll define its inverse, which is written as f inverse with this -1 here. Don't confuse that with to the power of -1. It goes from the codomain of f, so in this case b, these two are the same, back to the domain of f, so back to a in this case. And it's defined by this rule here. F inverse of f of x equals x. An equivalent definition is that f composite its inverse, so the composite function you get by combining the two, is the same function as the identity function, or the function that does absolutely nothing. It maps everything to itself. Intuitively, you can think of the inverse function sort of canceling out f just by taking the outputs and then mapping them straight back to where they came from. So our first example is kind of a little toy example. We've got a very simple function, f from a to b here, and both domain and codomain have only 3 things in them. So we see that 1 maps to 6, 3 maps to 12, and 5 maps to 18. F inverse is going to take in elements from b, so it's going to go from b, and it is going to take them straight back into a. And as you might guess, we can write all of these out. 6, 12, and 18 are in B. A's got 1, 3, and 5 in it. And F inverse is going to send everything right back to where it came from. Checking against the other definition, we see that if we take the composition of these two, we're going to start in A, end up intermediately in B, but still end up back in A. And if you draw out every step of the way, you get 1, 3, and 5 in the domain to start. We're going to pass through 6, 12, and 8, this set containing these 3, and end up back in 1, 3, 5. The path for each one is going to look like this, right? You can go back and cross-reference this against the diagrams I drew for both f and f inverse, and just confirm that combining the two, or running them both in succession, will get you to this. And you see that every element here has ended up back where it started. So 1's gone back to 1, 3's gone back to 3, 5's gone back to 5. And that's what we mean when we compose the two functions that are inverses. We get the do-nothing function, the identity function. All right, moving on to a bit bigger of an example. Let's say we got this function here, where its codomain and domain satisfy the properties we've talked about above. We'll just say they do. Not worry about that for now. And we know it's defined not by an explicit mapping, but by a rule. So f of x goes to x minus 1 all over x minus 2. So first off, we know, first of all, that f inverse should go from c to d, just by definition. That part's pretty easy. Trickier part is figuring out what the rule is for the inverse, sort of the inverse rule. And turns out there's a trick for this that is fairly straightforward once you understand how it works. So you start here with f of f inverse of x is equal to x. Now this is true by definition. It's pretty much how we define the inverse in the first place. So we know we can write this down. What you're going to do now is you're going to substitute f inverse in to the rule for f of x. So what you end up with is f of f inverse of x is equal to f inverse of x plus 1 all over f inverse of x minus 2. Make sure you understand how we got to this step. We took f inverse of x and plugged it in as x, right? Because it's in this position. Does that make sense? Make sure it does. Now we knew before that this is equal to x, so it's still equal to x, right? This equality holds. And then we just ignore the middle part. So we have x equals to f inverse of x plus 1 all over f inverse of x minus 2. And then we can simply solve for f inverse of x. What that looks like for this particular example is we're going to multiply out the denominator and bring it over here. So that gives us x f inverse of x minus 2x equals f inverse of x. And then we simply isolate all instances of f inverse. So we can move this to this side and move this over to here. And that gives us x f inverse of x minus f inverse of x is equal to 2x plus 1. And then we can simply divide out and get, factor out first, get x minus 1 times f inverse of x equals to 2x plus 1. And finally, f inverse of x equals to 2x plus 1 over x minus 1. Now, if you're curious, you can take this final rule here and feed it back into here. So essentially manually compute this nested function here. What you should get is x, because that's exactly how we found this new rule. So if you're still shaky on how this works, give that back substitution a try. All right, so this trick works for every function defined by a rule, as long as we know that it hits its entire codomain and it's injective. But what does injective mean, right? Why do we need it? And how do we figure out if something is injective? A function is injective if every input goes to a different output. So all of the functions that I talked about before, they were all injective. It's most easy to see that in the little toy example with the three inputs and 3 outputs that I had before. So if you're shaky on what this means, go back, you can look at that one. This function below is not injective, all right? This is because 6 and 12 both map to 2. And so not every input goes to a different output. Why is this a problem? Well, if we were trying to invert this, and we had 2 in our domain, well, now our codomain has 6 and 12. How are we supposed to map 2 back to something if there are 2 possible options? We can't. And that's why we need injectivity. We can't have these inputs that are combining into one output. Otherwise, if you try to invert it, you get an input that tries to branch out into 2 outputs, which makes it not a function. For a bigger example, let's look at this function here. It's going to take in real numbers, and it's going to go into the positive numbers. And take it from me, this function does hit its entire codomain. You can take in, for every number in its codomain, you can find something that maps to it. So that's not the issue here. The issue here is that this function defined by f of x equals x squared is not injective. Easiest example of that is if we plug in x equals 1, we get f of 1 equals to 1 squared, which equals to 1. But if we plug in f of negative 1, we get the same thing, right? Minus 1 all squared. That's also equal to 1. So if we were trying and write down an inverse, we'd have to think, okay, f inverse of 1. Is that 1 or is that minus 1? And there's no way to do that, right? We have this branching out thing that we had before because the same two inputs in our original function, or sorry, two different inputs in our original function went to the same output. However, once we decide to take out all the negative numbers from the domain of this function, right? If we trim down its domain, we say, nope, we're not going to allow negative numbers. We only have 0 here and the positive numbers. Then we're all good. Then we are now injective, because kind of the second choice for each possible output has been eliminated. You've only got the positive answer to it. So in this case, our inverse function just is defined like usual. It goes from the codomain of the original function, inputs from there, and it outputs back into the original domain. And we can even use the trick from before, where we say g of g inverse of x is equal to x, which gives us g inverse of x equals to, g inverse of x squared, all squared, equals to x. And now we can simply take the square root of both sides, because we know we're taking the positive answer to the square root instead of choosing between either of them. And that gives us g inverse of x equals the square root of x. And that's injectivity. So to recap, if a function hits its entire codomain and every single input maps to a different output, we can construct an inverse function that undoes the action of that function and combines with the original function to create the do-nothing function. And that's what inversion is all about. See you guys in the next video, and thank you for watching.